Hello everyone, my name is Cao Siyu. I am glad to share the paper accepted by 28th ACM CKDD to you guys. The title of paper is In Defense of Course-Set, a Density-Aware Course-Set Selection for Active Learning, sponsored by a Korean AI-oriented biotech company. These are the main contents. From the background, we should focus on the active learning and density approach. Active learning is famous for its loop. Different from both supervised and unsupervised learning, the active learning uses small labeled dataset and many unlabeled data as the input. The goal of the active learning is to pick out the most informative samples which improve the model performance. Usually, such samples related to high loss in training stage. Look at the figure. The classical active learning process starts from the model trained on a small labeled set. Then it predicts the unlabeled data and we evaluate the model. We allow the oracle to give the label for selected samples and add them in the labeled training set. And do the next iteration until the budget is used out. There are two traditional strategies to select informative samples, the uncertainty sampling and density-based approach. According to the entropy, loss, and confidence, uncertainty sampling developed the Bayesian uncertainty, loss, and nearest neighbor methods. While these cannot ignore the duplicate samples, so they waste the query budget. In the density-based approach, it uses the centered features to sample data, while such strategy always perform worse than the uncertainty sampling because they don't consider the difficulty of predict those data. So, the authors attempt to find a course-set-based method, but take the uncertainty into consideration. And the research problem we can see here from two parts. One is course-set approach is the promising diversity-based method, selecting the diverse samples based on the distance between samples. However, the approach poorly performs compared to the uncertainty-based approaches. And the second is which regions are informative for the sample selections. And according to those theories, the author gets some motivation. And the feature space based on the density estimation may contribute to the informative sample selection. Each domain with the samples have different levels of importance and influence on the models. If you select the course-set samples in the sparse regions, maybe we can pick out the data with both diversity and uncertainty properties. And to verify the assumption, they observe the correlation coefficient between the entropy and density, and also the loss and density. The density is based on the KNN method. There exist obviously negative relationships, which means the assumptions are correct. Samples with high entropy and loss usually have low estimated density, which means local sparse region. And this analysis shows that the sparse regions are more informative than the dense region. And also the samples are uncertain, suggesting that the acquisition should be focused on the locally sparse regions. Okay. The main idea of this paper is the density-aware coset approach. First, they calculate the density of each unlabeled data, and then they select locally sparse region samples by the coset approach training with the labeled data, and I'll explain the process in details. And first, the author need to get the density of all unlabeled data. They calculate the distance between samples and their surroundings according to the nearest neighbors method. But there are two computational problems. One is the high dimensionality of features of each sample in neural network will influences the distance calculation between samples. And the second is the large number of unlabeled datasets in the active learning. Estimating such density of each sample, the KNN method should calculate the distance to all unlabeled sets. That's a very big computation problem. So the authors created two strategies to solve the problems. And the first is the auxiliary classifier, and the second is the Hessian-based density estimation, and which means LSH, the local sensitive Hessian. How does the auxiliary classifier work? And it takes the large features of the existing network as input. Then the input factors are transformed to the low-dimensional normalized vectors, Zi hat, and Zi is a large dimensional input. And this is the loss of Zi with the omega t. And Yi is ground truth, and P is predicted probability given the Zi and the model parameters omega t. And the overall loss function with the auxiliary training can be represented as follows. And it is the sum of the original classifier and auxiliary classifier. And lambda here is the control factor. And the omega t hat here is the additional parameters of this new classifier. And from the normalization, here the L2 norm of the Zi hat is much smaller than the Zi. And thus the high-dimensional features can be compressed to the low-dimensional vectors. The authors achieved compress 512 and dimensional vectors into 16-dimensional in this approach. But we still have the problem of finding the k-nearest neighbors for all unlabeled data samples. And the samples can be hashed into k different buckets, and finding their nearest neighbors in each bucket instead of the entire data set. And it enables the efficient estimation for the density. And for the acquisition phase, they also use this method to optimize the process. And here the SI indicates the bucket number of the sample, and this value is concatenation of two vectors. And we got the bucket. And next, due to the coset approach, we get more samples from sparse and less from dense here, and label them and also transfer them into the oracle and label them. Here we get the processed data, and also density-aware coset can be complementarily combined with the uncertainty-based methods, because the proposed method naturally can prevent the selection of duplicate samples. And these steps are the traditional step of uncertainty sampling. Here are the experiments of two different tasks which can be see as the image classification, and the second is drug-protein interaction. And we look at it first. They also use the Sci-Fi10 and redundant MNIST datasets. And for the Sci-Fi10, they use the ResNet 18 as a backbone, and for the second, they use three-layered networks. And also, they compile their own approach with the 4 strong baselines. And the first two, LANLOS and NCENet, are based on the uncertainty sampling, and these two are based on the diversity-based methods. And from these two tables, we can see that their approach performance are always outperformed than the traditional baselines. And also, if the author combine the LANLOS, the uncertainty approach, and their own method, the performance can even be better than their own approach. And it can also proves that the density-aware coset approach can improve the uncertainty sampling method, and also the accuracy on the test dataset is very good. And the second is the regression type task. It is the drug-protein interaction, and they use the Davis dataset, and they drop two baselines which are optimized for the classification task, and the author use the deep DTA as a backbone. And because here the value in the tables are mean-squared errors, so the smaller the better. And we can see that their approach can achieve better performance than the others. And when the combination appears, the performance are the best compared to the above one. And so we can see the LANLOS method largely increased with the combination, and which are very good sign for the approach. And for the last part, analysis and conclusion, we also have a problem that if the DACS work with a small query budget, can it perform well as before? And the author also do the experiments. They reduce the cost of query and observe the results as the figures. And this yellow line is the approach, and we can see that they verify that the density-aware coset can work quite well in the small number of query settings. To conclude, first, the authors show that the sparse regions tend to include more informative samples than the density region. So they propose the density-aware coset approach, which select samples from both diversity and uncertainty aspects. Finally, the results reveal that it works well. That's the end. Thanks for your attention.